Yeah, hi everyone. This is just for recording. So this is the course optimization techniques, ENGG 6140, and section 2 at the University of Guelph School of Engineering. Okay, great. Thank you very much to everyone who for introducing yourselves. By the way, we will go and I'll say that please participate in the class and discuss and in the discussions and all of it. I don't want to be the sole speaker. I hate the classes where the teacher or the instructor speaks and no one says anything. We want to learn together. I will learn from you, you will learn from me. And so don't look at me as an instructor or teacher, look at me as your friend. We all are gathering together. We want to learn something. I will learn from you too. So you learn from me, I will learn from you. We all learn from each other. I might have some mistakes, you will correct me, that's fine. I will be happy to be corrected. And if I don't know anything, I will let you know. I don't know this part, let me look at it later, and I will talk about it the next session, or we can discuss it in the class and figure it out together, all together. So I want the class to be cool and fun, not just me, the sole speaker. Please, I appreciate your participation and ask your questions. Ask your questions whenever you have questions. You don't need to raise hand or something. You can say, I have a question here. I didn't understand this part, and we will all discuss about it. And please note that when you have a question and when you ask, this might resolve the ambiguity in someone other's head. So yeah, so I'm saying that your questions will help everyone. That's why I'm saying that feel free to ask your questions. I myself, when I was a student, I used to ask a lot of questions, and I believe asking questions help this everyone to understand much better. So let me share screen for the slides. So what I do, yeah, I'm using a tool just where I can also write on the slides, and you will see, I think, my notes here. Yeah, like you can see that. I will also upload the annotated slides and notes in the course homepage as well as course link. So let's go through the course introduction first, and then please let me know if there is any ambiguity or anything you want to discuss. So this course provides the main methods of optimization. As we said, we don't want to just cover only theory. We don't want to cover only practice. We'll cover both theory and practice. So, and we don't want to only cover fancy algorithms or the algorithms which are not going to be useful in practice. So we are going to learn the core algorithms in optimization, which can be used in both theory and application in industry, and also research. So this is this course, what this course is about. What do we start with? We start with preliminaries and background. We start with sets, norms. Before that, we have an overall introduction on optimization, We say, what is optimization? What do we want to do? Why do we need optimization? And all of these things. Thereafter, we go to sets, norms, functions, local, global minimizers, derivatives. So if you don't know these, don't worry. Don't panic at all. We'll cover these. We will cover gradient, Jacobian, Hessian, convexity of sets, and convexity of functions. And I will assure you that you will learn when you are learning these concepts, you will enjoy. You will enjoy uh, both the methods and also the concepts. And we will try to simplify definitions and all of these things. If there is theory, we'll try to simplify to understand it. But we will also don't skip the theory. We'll cover this theory in order to understand why the algorithms work. And then that algorithm is also going to be applied in industry and practice. We will introduce afterwards the standard problems, convex problem, linear programming, quadratic programming, semi-definite programming. Just we'll see what these mean. And then we go and cover linear programming. The simplex algorithm, specifically, we will focus on tableau method, which is one of the implementations for the simplex algorithm. We'll cover integer linear programming. We'll say what these are. So if you don't know what these are, don't worry, we'll go over them. And integer linear programming, we will cover a branch and bound method, which has a tree structure thing for learning, for finding the optimal solution. So we use a branch and bound method in order to reduce integer linear programming or simplify integer linear programming to linear programming. And then we use the methods which we learned for linear programming to solve the integer linear programming. In other words, we simplify or reduce integer linear programming to linear programming. We'll say how. We'll cover those. And then we will use whatever we learned for linear programming in order to solve the integer linear programming. We will also introduce Ghojogh-Kontaker. In short, it's KKT conditions. I think you might have heard of it. KKT conditions are very, very famous in optimization. They might seem scary, but they are not scary at all. They are very fun. We'll go over them, and you will see that they are very simple, very understandable, and yet very useful for optimization. And we'll go over Lagrangian function, also method of Lagrange multipliers. We'll go over these. Afterwards, we will cover unconstrained and constrained first order optimization. Previous to that, we'll learn what unconstrained means and constraint means. So we will cover every concept. We don't skip things and assume that you know that already. We'll cover those. After knowing what unconstrained and constrained mean, we will learn first order optimization. So we say, what is first order optimization? These are the optimization techniques which are based on gradient. And these are gradient methods. We'll also cover second order optimization. By the way, usually if you see many courses, they only cover unconstrained first order optimization, which is whose most famous algorithm is gradient descent. But we will also cover constrained first order optimization, because that will be more useful for your either for industry or research, because usually you have some constraints either in industry or your research, and we'll cover that, how to deal with that if we have constraints. We'll also cover second order optimization, which is also called Newton's method. If it has constraints, again, usually we have constraints, its name is interior point method or barrier methods. I don't know if you have heard of them or not, but we will cover them. And they can be useful in they can used to be solved to solve all convex optimizations. And we will say that we'll see that usually important optimization toolboxes such as CVX, and they use interior point method. They are second order methods. And if you see, for example, the course of Stephen Boyd at Stanford, I will introduce the link to you. It's just for interested. If you are interested in more things, you can look at that too. Optional. You will see that Boyd loves interior point method. Stephen Boyd is one of the important figures in or scholars in optimization, and he's a prof at Stanford University engineering school department. And if you see his papers, he uses optimization for doing lots of cool things, and he's mostly using interior point methods. He loves that. And then we cover important meta-heuristic methods. And we'll see why these are important. So until here, up to here, so these are classical methods for optimization. And these are mostly based on some math behind them. There is also meta-heuristic optimization where we say, what if what if the cost function is too complicated? Or what if we have too many constraints? An example is that, for example, if you want to optimize the aerodynamic structure of airplanes or something like that, these are very complicated optimizations. Sometimes it's very hard to use classical methods for them. Then we can use meta-heuristic optimization or meta-heuristic methods for these problems. We'll see how they work. We'll see, by the way, the meta-heuristic optimization is also called some area of soft computing, because soft computing has several areas. Soft computing has fuzzy logic in it, has some connectionist methods such as neural networks and these things. Also, fuzzy control. Soft computing also has meta-heuristic methods. They're sometimes also called evolutionary algorithms or evolutionary methods. But evolutionary methods are a sub-area of meta-heuristic methods. And we will cover those, so don't worry about that. We will cover some important algorithms in meta-heuristic optimizations, including genetic algorithm, which is inspired by Darwinism. It says that, or evolution. Usually every generation is in a way better than the previous generations in evolution for adapting to something, to the environment. So we use such concepts for optimization, and you'll see it's very interesting. Usually meta-heuristic methods are based on some story, or their algorithms are based on some story. For example, we have whale optimization. So they are based on the story of how whale lives in the sea, or how we have wolf optimization. It says it's based on the story of how wolves can attack some animal or something. How do they interact with each other? How do they look at each other? How, for example, a wolf comes from in front and two wolves come from back and they attack the target, something like that. Usually they are very cool stories behind the meta-heuristic methods. We'll cover particle swarm optimization and also probably simulated annealing. So in short, if you want to know what particle swarm optimization is, we will cover that in more detail the next lecture in this session. But it's just saying that if we have several particles, how can they collaborate with each other in order to find the best solution? So there's a landscape and we have some particles on it, and this landscape goes up and down, and we want to find this the smallest height, the shortest height in this landscape. These particles search, we randomly throw the particles in the landscape, they search, they tell each other, oh, I found something here, I found something here, and then they, with the help of each other, they find the best solution. I will explain this in more details in some other slides that I have in this session. Simulated annealing is also saying that we have, it's like something that is very hot, and in engineering, I think, especially mechanical engineering, people might know something about that. Also, it is in physics too. So you say you have something very hot, you cool it down slowly, and you reduce the temperature, and by reducing the temperature, you become more stabilized, and you will, with some algorithm, you converge to the best solution. And this is called simulated annealing. I think should have a D here. Okay. If time allows, we'll cover distributed optimization. The most famous algorithm in distributed optimization is ADMM. It's short for alternating, I think, distributed. Let me search it. I forgot what is it short for. Yeah, direction method of multipliers. And we'll see why it has this name, alternating direction. We'll see why. And method of multipliers, we'll see why, because it's based on Lagrange multipliers, and based on the method of Lagrange multipliers and KKT that we already have studied in several previous sessions of that session. Also, so what is distributed optimization? It says that assume I have several optimization variables. We will see what optimization variable is. So don't worry about that. We'll cover that. Assume we have some variables. We can distribute the optimization over these variables rather than one variable, and we can parallelize it somehow, make it parallel, and that's why it becomes distributed. And then it's very related. Its idea is very similar to federated learning. I don't expect you to know what federated learning is. Federated learning is a concept in machine learning. Just, it's for your knowledge, I'm saying that. Federated learning says that assume I have a neural network or something which learns. It has some parameters which are learnable. We want to learn the parameters. We can distribute data to some nodes or some servers, and then we can these servers will learn or update the parameters based on the data that they have, and then they send their parameters to a central center server, and that central server combines them, accumulates them somehow, or averages them, and then it sends the updated parameters back to the distributed servers. So the servers, again, it's very similar to what one of you guys said, big data. If you have big data, you can divide data to some pieces of data, and then they optimize some models in some servers. The servers optimize that, send it to some central server. We combine them, we send it back to them. This procedure repeats. This is federated learning. And as you see, these servers, small servers, they don't see each other. They only see the central server. That's why federated learning can be used for privacy and security too, because we don't want these to be seen to each other. Only central server can see them. So this is federated learning. And the same idea, it's almost the main idea behind all distributed algorithms. In distributed algorithms, there are several things. For example, we have some nodes, and the nodes communicate to each other somehow. And these nodes make graph. So based on the connections of each other, they make some graph, some kind of graph. It might be fully connected graph, or it might be every node is connected to its two closest neighbors. So we can have some kind of graph, and the nodes of the graph talk to each other. This is usually distributed algorithms are based on that. And distributed optimization says, okay, now we have some variables. Let's distribute them to some nodes. Again, similar to federated learning, to some servers. They do their optimization and they send it back to me. I combine them in some variable, and I send the variable, the combined variable, to them again. They optimize it, send it back to me. This procedure repeats until convergence. So this is the idea behind distributed optimization. And one of its most famous algorithms is ADMM, alternating direction method of multipliers. Okay, and I'm not sure if we have more time than that or not. If yes, we can cover some other cool things too, like subgradient. For example, when we will see what these mean. For example, assume your cost or the function that you are optimizing. So if it is a smooth, it's like this, for example. So it's smooth everywhere. But what if it's like this? Here it's not smooth, like absolute value function, right? Absolute value function is like this. At 0, this function is not smooth. And smoothness is because it's not smooth, it's so obvious, because it has a corner here, as you see. And when it has a corner, it means that the gradient is not defined here. The derivative is not defined here, right? So we can use some other concept named subgradient, and it's also related. It can be related to L1 norm and all of these things. We will cover those if time allows, and I think time allows that. If not, that's fine. We will see how much we can cover. And so the sum schedule, that is tentative, but we can say that again. Initial weeks we cover preliminaries, and then we cover linear programming, simplex method. I'm not very strict about the fact that we cover this in this week. We cover that in this week. We'll go over the lectures one by one, and if we have extra time, we will cover more things. And you don't need to be worried to that if extra things are added to the course, because this course doesn't have a final exam. This course has a midterm exam, so some things, initial things you will have exam on, and then the later things will not have any exam for them. They might have assignments for them, but you will learn cool things, so you don't need to worry if we add more things. There's not going to be any final exam, but we'll have project, and I think you will learn a lot in your own projects. So linear programming, simplex method, tableau method, integer linear programming, and then, as I said, KKT conditions. Midterm exam will have around week 6. It might be a bit week 5 or week 7. It will be around week 6. We'll discuss that. And again, unconstrained and constrained first order method, unconstrained and constrained second order method, meta-heuristic optimization, distributed optimization, and if time allows, more things such as L1 norm optimization, subgradients, non-smooth optimization, and all of these things. Any questions so far? Why am I the sole speaker? Anyone?
It all looks. I'm excited. I've been listening, and
Yeah.
it all looks great. I'm ready to dive in. And yeah.
Okay, that's great. Thank you very much. Yeah. Does everyone feel the same? Please let me know either by saying that or writing in a comment in the chat or whatever. Feel free to let me know your opinion. We can
It all
readjust.
seems straightforward to me so far.
Okay, that's great. Others have the same idea. Please feel free to let me know if there's anything you. I will appreciate your feedback, and I will also apply your feedback, your opinion on the course outline and whatever we are gonna cover. So as I said, we are gonna learn together. I will learn from you, you will learn from me, we'll learn from each other. Okay, and so course materials, lecture notes will be provided to you. Of course, we'll have organized lectures, and I have a tutorial paper, and you can see that. Let me share screen if by going over this. Just give me a second. Yes, the link is provided in the lecture. Also, I can put the link here in the chat if you would like to have a look. Yeah. Okay, let me share screen for that. Yeah. Okay, as you see, I previously had written some tutorial paper. I love writing tutorials. You can see my tutorials, my other tutorials, if you would like, on different topics, including machine learning and dimensionality reduction, manifold learning, and all of these things. And one tutorial that I had written before with some co-authors, some of my professors, is this. You don't need, it's not mandatory to read this. It's just optional, because we will cover the things. I will put the important things in the lectures, but if you are interested, you can read more in this tutorial. There are many other good tutorials too. It's not the only tutorial on the internet, but this is one of them. You can, optional, you can take a look at it. It doesn't have much about linear programming in it and the simplex method, but other topics are mostly can be found in this tutorial. I hope you enjoy that, and if you find any mistake in it, please let me know, and we'll apply that, we'll correct that, and submit another version to archive. And what is archive, if you're not familiar with that? It's just a public, I can say it's a public journal. It's open access thing that people put their research papers in an archive, so everyone in the world can have access to that. And this is originally for Cornell University. So this is archive, and this is a tutorial paper on archive. So this is one thing I wanted to introduce this paper to you again. Don't worry about that if you don't have time to read that, but it's optional. Hopefully you will enjoy reading that. And I will also be happy to discuss the concepts in this paper and other papers with you if you would like. And by the way, it's not just for research. Don't think of this tutorial paper just for research. I believe that this paper can be useful for industry too, for both industry and research. Okay, now let's go back to the slides. Let me share a screen for the slides. So this is a tutorial paper that we introduced. Again, as I said, the linear programming is not covered in that paper. Just we have pointed to that. It's not details of it. And there are for interested students, these are optional, not mandatory. Convex optimization 1 and 2, if you search that on the internet and YouTube, you will see it's in the channel of Stanford University. Many universities have their own channels on YouTube, and as I said previously, Professor Stephen Boyd at the University of Stanford, he teaches convex optimization. There are 2 courses, and they have there is a playlist for the 2 courses back to back. Convex optimization 1 and 2. If you search that on the internet, one of the first playlists which come up is that playlist which has both courses in it, and it's a good course to look at. Convex optimization 1 of Stanford University covers mostly just the interior point methods, the second order methods. Do you remember here? This, this bullet point. This bullet point was second order, and as I said, when we have constraints, it's interior point method, also called barrier methods. We will go over them step by step with simple language, not complicated, but we'll understand why it is working. The most important thing is that we understand why this is working and how to use it in practice, and also we will understand what's the core meaning of that. And this is mostly covered also in the course optimization 1 of Stanford. Also, some of the preliminaries also are covered in the optimization 1 of Stanford. Again, as I said, that YouTube channel optimization course on YouTube is just optional, not mandatory for interested students. And we'll also optimization 2 of Stanford, I can say goes to several things. It covers non-smooth. Do you remember here? I said there's non-smooth, and if it is non-smooth, we have subgradient rather than gradient. It is covered in optimization 2 of Stanford. Also, I remember distributed optimization. This bullet point is covered in optimization 2 of Stanford. Some first order methods, although Professor Boyd briefly mentions first order methods in his first optimization course, but in his second course he goes more deeply in the first order methods, optimization methods. And yeah, these things, and I believe it's very useful, optional if you would like to look at them. Now, additional books, not mandatory, but I think it's good to look at them. Boyd's textbook is very famous, especially for people from engineering who work on optimization, focusing on convexity and second order methods. Again, this book, I think it's called Convex Optimization, is mostly for Convex Optimization 1. It usually doesn't have, I think it doesn't have Convex Optimization 2 of Stanford in it. And it has interior point method in it. And also the books of Professor Yuri Nesterov. He's very good in optimization, especially his book is mostly focused on first order optimization. And he has two courses. He has 2 books, textbooks. One of them is Introductory Lectures on Convex Optimization, a basic course. So he has eliminated many of the proofs and theory in it, just a less deep look at the algorithms in his book. But if you want to know more about the theory and the theory behind the algorithms and more proofs, they are in lectures on convex optimization. So he has 2 versions of one book. One of them is has more theory. And Yuri Nesterov is one of the figures, one of the main scholars in optimization, and he's great, like Boyd. And there are some research articles in the literature. You can look at them. Courses website we have, so classes will be online via Zoom. The link, you have it. And we'll probably make it a Microsoft Teams group. When I was in Waterloo, I was studying here, we had Piazza. Piazza was very good for question answering, but apparently we don't have it here. So one option is we make a Microsoft Teams group, which we can ask questions, make discussions there. Or we can do that in Course Link too, but I think Microsoft Teams is a better option for that. And we can add, I can make one chat in Microsoft Teams and add you by adding your emails. Please accept that and come to the chat, and then we can ask our questions offline. Of course, you can ask your questions in the class too, but when we are not in the class, we can ask questions on Teams. There is a course website I have made, and I put contents, lectures, and assignments on both this website and also both course link and here. You can look at, but I think the announcements on all of those other things will be in the course link, but the contents and will also be put here on the course website. Well, I'll probably upload the videos to YouTube, to my YouTube channel, but don't worry about that. As you saw, I didn't record when you were introducing yourself, so I'll not include your personal information in the videos. So I respect your privacy. And I said that. So about the course evaluation, we'll have assignments. We'll probably have 3 assignments. I should discuss it with the TA. You'll have one TA too. I think we'll have 3 assignments probably, but I need to discuss with the TA too. The midterm exam it will be around week 6, and we'll discuss what will be covered in the midterm. And we have a course project, so 40% of the grade will be course project, 30% will be midterm, and 20% will be assignments. And by the way, for the midterm, don't worry, I'll not make it super complicated. As long as you attend the classes, you understand what we are talking about. Also, if you solve the assignments, we will provide you the answers to the assignments after the deadline. And you understand assignments very well, the midterm will be similar. It will be easy for you. So you don't need to worry about that much. As I said here, the main focus of this course is for you to understand optimization. We don't want to suffer. We want to learn and have fun together. And the course project, you will, I think, will make you will make groups based on the number of people. I think we can have the groups of 3, but let's wait until the class is stabilized, and then we can decide on the number of people per group, and then you will make groups, and you will have you will pick a project topic, and you will work on that, and you will have a report for that. So you will submit both reports, and also you will have a group presentation for your project, and in the last weeks of the semester during the class time. So the presentation will be 10%, and so please, everybody in the group, it's good to have all of them speak in the presentation. Also, the course project, the report, as well as how you have done the course project. We will evaluate based on that, and I hope you have fun doing the course project. It will be about 40% because this is a graduate course. So course project is important. Bonus points, will have definitely bonus points, especially participation in the class. Participation is not mandatory. It's, as I say, it's bonus points. How do I know the participation of people? If they discuss, because I think I'm not gonna ask people. I don't like that. If you are here or not, I want you to discuss, participate in the discussions, ask questions, answer questions. If someone asks a question, I will answer, you also answer. Say, I have a comment on that too. Or if you have a question, a follow-up question, feel free and jump to my speech and don't let me be the sole speaker. Say, I have something here I want to say, or I need clarification here. These I really like us to. I want it to be a discussion based. Honestly, I think if I only speak, it will be boring, and I don't want that. I want it to be a discussion based class. So please feel free to ask questions whenever you want. Participate in the classes, in the class discussions. Answer questions, ask questions, and all of these things, and we'll have bonus points for that. Don't worry much about your marks, as I said. As long as you attend the classes, you understand what you're saying, you ask questions whenever you don't understand something, that's fine. And do the assignments on time, and also understand the assignments, and you will do great in this course, and you will have fun. Don't worry much about marks. I want you to focus on understanding. Focus on understanding the materials of the course. Again, we want to learn important practical optimization methods, useful for both industry and academic research, both of them. About the theory and practice, we'll learn some theory to understand why these methods work. And we'll also learn how to use them in practice for practical usage. So we'll cover both, and it will be useful for both interests in practice and theory. And again, ask questions whenever you don't understand. Don't want to be the sole speaker. There are some references that I had mentioned. This is the tutorial. This is Boyd's book, Convex Optimization. These are the two books of Nesterov, which were mostly focusing on first order methods. So, okay. And by the way, we'll have breaks in the every session, about 15 to 20 minutes, maybe 15. And then, in the middle of the class, and then we'll continue. So I think it's a good time for break. But before that, if anybody has a question or anything you would like to say, please let me know. Anyone?
I was just curious. It's a bit unrelated, but the photo in your background, it's like cubism. Is that your photo on the wall?
Which? Yeah, yeah. Honestly, I'm in the lounge right now. Yeah, and this is
No, it's in the
picture
lounge. I thought you might have been in your office. That was your.
No.
It's like looks like Picasso. I thought you were a fan.
Yeah, I think it's cubism, right? Exactly. Yeah, it's Pablo Picasso. Yeah, as you know, it's the style made, created by Picasso. And as you know, yeah, thanks for noticing. That's very interesting. Yeah. Of course, this is a copy of the Picasso's picture. Otherwise, it would be very expensive.
Is the presentation that's online then? So I guess each group member then presents just over Zoom in turn then?
Yes, exactly. You will prepare some slides, and we will decide how much time we will assign to each group, and then you will come and present what you have done, what are your findings, whatever you have done. And yeah, it will be simple, not very complicated.
Sounds good.
Great. Anyone else has a comment or question? Okay. What?
Yeah, sorry. I don't know if you mentioned this, the test, will it have any sort of coding in it?
The test, the midterm test, you mean? I think in assignments I will put some coding, but in the test, I'm not sure yet. I need to think about it, but I will get your feedback on that, and maybe decide based on your feedback. I'm asking the whole class, what is your opinion? Would you like to have coding in your exam?
Yes, we can, like only if it's like we can use any languages to solve the problem, right?
Okay.
Like
Yeah,
for
but
assignments, if can we use C++ or Python? Like people prefer Python, even I prefer Python, but just to get my hands dirty, we can also use C++.
okay. Some
I think
people are
we-
saying no.
I think we'd have to see the material, I think, before we can make that decision, because
Yeah, I understand.
yeah,
Yes, some people are also saying no. We can say we can have coding on assignments, not to be stressful. What's your opinion? Maybe. Yeah, I think because it's good to have coding at some points in somewhere in the course, so you can yeah, I think you can understand how to use them in practice in assignments. But because I really hate to make the course stressful, I want everyone to enjoy the course. Maybe we can put coding in assignments and have a midterm exam without any coding, maybe something, because I noticed that people are against having, some people are against having coding in the exam. I understand why, because it's a bit stressful, it's time limited. Yeah, I understand. But yeah, about the language of coding for maybe assignments, is everyone comfortable with Python or no?
I'm comfortable with Python, but in assignments, I think coding is fine, because you can always, go on GitHub or find someone who's done something similar and then kind of work off of that. But in a test, when you're under pressure, it's very hard to, like I like to search on the internet, and there's always multiple solutions to a problem, right? When you're coding, you can do it in 5 different ways. So I think that becomes very stressful in a test situation. But in an assignment, at least for me, it's not an issue.
Okay, that's fine. Sure. And by the way, okay, that's fine. We can have, maybe, as everyone agrees, we can have Python as a language for coding, and we'll have that in the assignments, not in the exam. Also, one very small question I have, because of I want to put the videos on YouTube. I think it's it's not possible to erase all the names on that. Is that fine? That with everybody, that maybe the names are in the video or not? If you have any comment on that, please let me know. So I think that I'm not sure whether is anybody has. Please let me know if you're not comfortable with that. Let me see. Okay. Sure. Thank you very much. Yeah, as I said, I didn't record the first part where we were introducing ourselves. And if anyone has any is uncomfortable with that, please let me know either here or later offline. So I can, but it will make it a bit hard for me. I need to use the video editing tools in order to blur or hide that your name on that. But that's fine. I'm totally fine with that. I want you to be comfortable. If you are not comfortable with that, please let me know and I will hide that in the videos. Sure, great. And again, please participate in the in the discussions and ask questions, answer questions. If, for example, someone asks a question, don't wait for me to answer. You also say your opinion or your answer on that. I really love these kinds of classes and courses where everybody wants to be in the class and course. And don't look at me as the professor or something. I'm your friend. We want to learn optimization together. Any other comment before the break? Okay, that's great. I think let's have a 15-minute break and come back on maybe 8:45. Is that fine?
Yeah, works.
Yeah, great.
Yeah.
Okay, have fun and we'll come back.
Thanks.
Thank you.
Thanks.
Marzi, I will answer your question after break. Sure, I will answer you. Thank you. Okay. Again, sorry about waiting. So there are two, before we go to the preliminaries, there are two questions on the chat. One of them is, what program software we will use for assignment? So if you all agree, we can, I think, work on Python. Python is a very simple language and very helpful for both industry and research. I don't know if anyone has any problem with that or not. I think it's good that you get familiar with Python. Also, there is another question saying that for projects, will you decide group members or we can choose? You can choose. I don't force anything. You can choose your group members and based on your interests. Okay, great. So let me share my PDF here. Again, these things happen in virtual classes when I don't know why the share screen of my thing is not working right now. My tablet thing, which I'm writing on. That's fine. Okay, so let me try one more time. Okay, yeah, I think it's worked. Yes. Okay, I'm happy it worked right now. So let me change the share screen. Okay, can you see that? Can someone say if you can see that or not?
Yes.
Wait, what are
Yeah.
we looking for?
Okay. You mean, well, I'm writing it here. Can you see that?
Oh, yeah, I can see that.
Okay,
Yeah.
great. That's great. Okay, thank you. So let's go over the preliminaries. Again, feel free to ask me if there's any question. What is optimization? So optimization problem. Assume we have a function. And what is a function? Function is something which takes some input and brings some output. And when we say in function in mathematics, we can't have two outputs per one input. So for example, you get it's not, if you consider a black box where you give it a caret, it gives you high. If you give it a a caret again, it gives you by. So it gives, so for one input, which is caret, it gives you two things, two outputs. It's not a function. We can have, it is possible to have one output for two inputs. For example, you give it a caret or you give it an apple. For both of these, it gives you high. It's possible, such as this function that you can see here. This function for two outputs, it gives you one input. But it's not possible to have something like this. This is not a function, right? Because for the same input, you have multiple outputs. This is not a function in mathematics. So this is a function. A function gets an input. So we say a function f gets an input and maps it to some output f of x. This is a function. And this input, which is the argument, this input can be either a scalar, a number. When we say a scalar, it means a number. Or it can be multidimensional. It can be a vector, it can be a matrix. And this function also, the output can be a number, a scalar. For example, in this example that you see here, in this example, you have one input, for example, one scalar input, you have one scalar output. So, or you can have multiple inputs and put them together to make it a vector. So you can have multidimensional input and a scalar output or a multidimensional output. You can have different combinations. So we have a function which we want to find its minimum or maximum. So this is a function. This is a function. Its minimum is here. This is a function, right? Another function is this. We want to find its maximum. So we want to find its minimum or maximum, and we call it usually a cost function or an objective function. Why do we call it a cost, especially when it is minimization? When we say minimization, it means that we want to minimize the function. We want to find the minimum. We usually call it a cost function because it's a cost of something, and we want to minimize that cost. For example, the amount of penalty that a system gives you, you want to minimize that penalty, something like that. And you can model that penalty by a function of its inputs. And you can also maximize a function. And we can usually when we want to maximize, we don't call it cost because we usually don't want to maximize something. We usually call it objective function. For minimization, we also can call it objective function. And for an example for maximization is the profit of a company. We want to maximize that. We want to find its maximum. So we want to either minimize or maximize the objective function, right? So again, example for minimization, error. For example, error of some airplane structure from the perfect aerodynamic structure. Some error, we want to minimize the error. We want to find the perfect structure for the airplane in order to minimize its error or some cost. Maximization, such as the profit of the company or anything which we want to maximize. And we can get philosophical and say all life is optimization. You can see, if you look at it very precisely, you'll see that I'm right. I'm saying that all of your life is optimization. You want to either minimize the cost of something or maximize the profit of something in any aspect of life. And also this optimization of life is not simple. It might be simple sometimes, but it's usually multidimensional. It's usually complex. The cost function, which you want to minimize or maximize in your life, is usually complicated. Its input is usually multidimensional. You can't say that, okay, my happiness is only based on my wealth. No, your happiness is based on your wealth, your mental health, your many different things. your love, whether whatever. So your happiness is based on many different factors. Therefore, these factors, you can put them together and make it a vector or matrix. Therefore, optimization of life is complicated. Also, all machine learning, all artificial intelligence, especially it's machine learning, is optimization. Why? In optimization, what is machine learning? In machine learning, you have a model, a mathematical model, and that this mathematical model wants to learn something. For example, in machine learning, usually you do one of these tasks. You usually regress, or you, for example, classify, or you cluster something. I will tell you what these are. Or you have reinforcement learning, decision making, and these things. And what are these simple examples for each of these? For example, for regression, you output something continuous. So you want to predict, so based on some inputs, you want to predict something. This prediction is called regression. And usually this prediction is a continuous number. It's not discrete, it's a continuous, it's a range of numbers. An example is that you want to make an artificial leg for people who don't have legs, to help them. Then, for example, you can get the, I think ECG, right? The signals from the muscles. I think it's called ECG, I'm not sure. But you get the signals from the muscles and from a healthy leg, and you will measure the degree of the knee, for example. And so you can say that based on this muscle pressure or this nerve signal, this angle of knee is required. And you will make a lookup table. Of course, you can't cover the whole range. You can have a lookup table. Then, based on some of the measurements, you will learn a regression model, which can predict for every nerve signal that it gets. And the interesting thing about regression is that it can interpolate. It means that it doesn't only memorize the table that you gave it. It can interpolate between these. For example, if the nerve signal alpha gives some angle, if the nerve signal beta gives another angle, something in the middle, gamma, let's call it gamma. Nerve signal gamma was not seen in the training, in the lookup table that you gave to the model, but it can predict what angle of leg you need for that. So this is regression. And as you see, we can model a regression by optimization. Why? Because we are saying this to the model. Hey, model, when you get this signal, nerve signal, your output should be this angle. If you give me another angle, your error should be increased. So you want to minimize this error of regression. If, for example, this nerve signal is supposed to give you degree 45 degrees, if you give me 50 degrees, you have 5 degrees of error. If you give me 60 degrees, you have 15 degrees of error. So try to minimize your error. This is regression. What is classification in machine learning? It says that, okay, now I want to output some discrete values in some discrete categories. I don't have just continuous. As you see, classification is a special case of regression because regression was continuous. Classification is regression, but output is only belongs to some categories. And these categories are usually finite, and the number of them. And as, for example, an example is that you want to classify two types, all the fruits to either cucumber or apple. And you'll train a model which can classify or discriminate the fruits to apple and cucumber. And you please tell me, soon I train a model which learns cucumber and apple. And now after training is done, I give an orange to it. What will it predict, do you think? What category will it assign to?
depending what it's trained on, but most likely the apple.
Yeah, because as I said, assume that the only two classes are apple and cucumber. And as you said, the orange that you give is more similar to apple. So it will say the orange is apple. But if you add another class, yeah, in the chat also someone said apple. Thank you. So if you have another class of orange, then it can correctly classify between orange and apples. So this is what classification is. And classification is also all of it is optimization. Why? Because you tell the model, if I give you something similar to cucumber, you're not supposed to give me the class apple as your output. If you do that, I will penalize you. I will give this is an error. So I want to minimize this error, saying that if you get cucumber, you should output cucumber, the label of cucumber. If you get as input apple, you should output the label of apple. Otherwise, there is a penalty, and I want to minimize this penalty. As you see, all classification is also optimization. Another thing is clustering in machine learning. Clustering, the difference is very interesting. Clustering means that I can explain it with some simple example. Assume you have a baby, because machine learning is like a baby. You want to train it in order to understand things, because the baby doesn't know anything. You have a baby, and again, you want the baby to learn the difference of apples and cucumbers. So in a classification problem, you tell the baby, you show 100 cucumbers to the baby, say, hey baby, this is cucumber. This is cucumber. Another cucumber, you show it to the baby. This is cucumber, cucumber, cucumber. Now you also show 100 apples, different apples, and say, this is apple, this is apple, this is apple. So you are saying the label to the baby. You're saying that this is cucumber, this is apple. Now the baby gradually learns that, oh, this is cucumber. When I see something similar to cucumber, I say, this is cucumber. And when I see something which is apple, this is apple. Usually, babies learn languages by something like that. Another case that you respect the understanding of the baby itself, and you don't tell the names to the baby. You just combine the apples and cucumbers on the ground, and you tell the baby, I know you're smart. I don't tell you this is apple, this is cucumber. You please, based on their colors or their patterns, whether they are thick, whether they are round or something like that, separate them into two groups. The baby puts the apples, looks at them, says, oh, apples are round. It puts the apples together, and it puts the cucumbers together, so separates them. But the baby doesn't know that the name of this group is apple. The name of this group is cucumber. Actually, it doesn't care for it. It says, I don't care whether it's called cucumber or chair. I don't care. I know that these patterns are similar, these patterns are similar. So I separate them. This is called clustering, and it's unsupervised because we don't tell the name or the label to the baby. And usually babies learn the patterns in life in an unsupervised manner or in clustering. Languages supervised, they learn the words, but the patterns of life, kindness or these things, and in an unsupervised manner. And as you see, this kind of clustering, which I said is doesn't use any labels, is also optimization. You say to the model or to the baby, cluster them in a way that the difference of patterns of the things that you are separating, their patterns should be similar. If the patterns are not similar within a group, you should be penalized. So you have an error or penalty or cost function, and you try to minimize that in order to have similar patterns within each group. Again, clustering is all optimization. And you have reinforcement learning. Reinforcement learning or decision making. Reinforcement learning in machine learning is nothing but it's very similar to how you train a dog. How do you train a dog? You say, hey dog, sit, sit. When you hear sit, you should sit. If or when I come to the home, you should come to me. So when you see the environment in a way that I come to the house, you should come to me. So you see, this is if this happens, your action should come into me. If you hear I say sit, you should sit. And how do you train the dog? You reward it. You give it a reward, or you penalize it. For example, if you say sit and it stands, you penalize the dog. You don't give the food to it. But if you say sit and the dog sits, you will give it the food. Gradually, the dog learns that by hearing the word sit, it needs to sit. This is so based on rewarding, positive rewarding or negative rewarding or penalizing or giving the positive reward, we can train a model like a dog. And this is called reinforcement learning. And reinforcement learning is also optimization. Again, so you have some penalty. As you see, you always have some cost function or penalty. You say, okay, when I say, when you see such an environment, when I come to the house, you should come to me. Otherwise, if you stand still, it's a penalty to you. You need to minimize the penalty. So this is, as I said, all machine learning or artificial intelligence is optimization. Again, as artificial intelligence is optimization, intelligence itself or life itself is also optimization. And as you can see that artificial intelligence is imitating or mimicking the intelligence itself. That's why both are optimization. So the variables, the inputs of the function that we are having and the function that we want to either minimize or maximize, they're called objective variables or decision variables or optimization variables. They're different names for the same thing. For example, the function x squared. X is the argument. You can say argument of optimization or objective variable. Objective variable. This is the cost function, and this is the whole function. And you either minimize or maximize. You usually write the argument under minimize or maximize. And here the minimum of x squared is 0. So its argument, we usually show it by a star. X star is 0, and f of x star, which means the minimum value of this function is 0. We'll see some other examples later. And please feel free to ask me, interrupt me if you want to discuss something. So the optimization problem can be univariate, meaning that the optimization problem has only one scalar variable. As I said, if it is a number, scalar. In this course, I usually show scalars not bold, and with a small case. Scalar. And the optimization problem can be multivariate. What does it mean? It means it has several dimensions, the variable. So for example, we have n of them, n dimensions, and we can put them together to make it a vector. And what does it? This is transpose. Usually, so this is this vector, x1 to xn. And when I want to write it in a line, I usually put it in a row-wise, and I put a transpose, which means that it is a column vector. And I show the vectors bold, usually bold, and a small case. Usually, okay, by default. We can put them together as a matrix. x11, x1n, xm1, xmn. So it can be a matrix. I usually write matrices bold and with capital case. Okay. Here, for example, as you see, it's a vector x transpose x. And what is x transpose x? So x transpose is this, x1, xn, x1, xn. If you multiply this together, it will give you this x1 squared plus x2 squared to xn squared. And this is, as you see here, this is a quadratic function. I have shown the figure here. So you have two variables, x1 and x2. These are the inputs, and it becomes like a bowl. The bowl goes up, and this is f of x. We want to minimize this. Its minimum here is 0. So x star is 0, 0. This 0 is for x1 star. This 0 is for x2 star, right? And f of x star, as you see, f of x here is a scalar. It is at 0, 0, the function is 0 itself. We can also show it using lines. So we can show it, look at it from above. So look, if you look at it from above, it becomes like this. You can see these are what these lines mean. It means that on each line, the value of function is the same. So here, for example, the value of function is the same. Then here, it means that the bowl is coming up. And this is a function, again, at 0, 0. The function is minimum, right? Okay. The optimization problem can be unconstrained. What does it mean? Assume, for example, I want to minimize this function, or another function. I want to, if it is a scalar, I want to minimize f of x squared. It is this. Only I have a function and I want to minimize it. This is unconstrained. There is no restriction on x. No restriction on x, right? But if there is a restriction on x, so as you see here, for example, restriction on x. This restriction or these restrictions are called constraints. Restriction. For example, we say that, okay, I have two variables or a multivariate variable. So it's a two-dimensional variable. You can write it with two scalars, right? It's a column vector of x1, x2. I have a function, x transpose x. It's a quadratic function. You can write it here in this way. This is the vector form. This is the scalar form. Subject to, when we say subject to, it means the constraint or the restriction. We have two constraints here. We have two constraints here or restrictions. One of them says when I want the x1 plus x2 to be less than or equal to 8, always. 2x1 plus x2 squared be equal to 16. So we are kind of restricting the domains of the x1 and x2. How? We are showing it here in this figure. So for example, x1 and x2. What is this function? Let's first draw this function. This function is this line. I can tell you how I obtained this. So I put 0 for x1. What does it give me? x2 becomes 8 over 2, right? So here I say, well, if x1 is 0, 2x2, let it be this. Consider it as a line for now. x2 becomes 4. So it means when x1 is 0, x2 is 4 here. Now, once I give it x2 0, it gives me x1 8. It's here. It's a line. We know it's a line because both are scalars. They are not quadratic or something. So a line passes these two lines, these 2 points. And when we say, I think there is a mistake. Assume this is equal for this figure. Sorry about that. I will correct that in the slide. And yeah, this is this, I guess. Okay. Now for this this is quadratic. As you see, x2 is quadratic in x2, but it's scalar x1. Set x1 to 0 once, x2 becomes 4 or minus 4. These two points. Now give x2 0, x1 gives 8, which is here. Now this is a quadratic function, which I drew, passing through all these 3 points. How do I know whether I should, it's in an inequality. Do you see that? So it means that either I'm here inside this quadratic function, or I'm outside. How do I know whether I'm inside or outside? We can put a number, for example, 0 and 0. 0 and 0 is less than 16. Means that it should, 0 and 0 is less than 16, correct. So it means that this region should include 0 and 0. So it's here. So I'm here in this region. It means that the second constraint is saying that I'm here. So let me erase this. It means that I am here. I'm inside. Also, I'm on the line. The first constraint says I'm on the line. Do you see that? So it means that here, this is the line, and I should be here. So only here, because this part of the line and this part of the line are not inside this. So it means that the only feasible or acceptable domain for x1 and x2 is on this region, this line, this part. And on this, I should minimize x1 squared plus x2 squared. So I should see the function x1 squared plus x2 squared. When is it minimized on this line? For example, here, I think the answer will be somewhere around here. I haven't calculated that, but we can see that it's either here or around here, because when we become here, it becomes 8 squared plus 0 squared. It's very high. 8 squared is 64. Here we have 4 squared plus 0 squared, right? It's 16. So it's either this point or somewhere around close to it. This is the answer. So this is a visualization. I wanted you to understand what constraint means. You can have many constraints, but the more constraints you have, the more complicated it becomes. But note that you shouldn't have contradictory constraints. For example, if you say minimize f of x squared, assume it's a scalar, subject to, I can write subject to short by st, okay? This x is less than 2, and this x is more than 16. Consider this problem. These two constraints are contradictory. It means that the feasible region or the domain, acceptable domain for x is nothing. It belongs to nothing. In this acceptable region, where does this function, where is it minimized? Nowhere. So this optimization problem doesn't have an answer because the constraints are contradictory. The constraints should have some kind of overlap, like this, like here. The two constraints have some overlap. Okay, now optimization versus search. Guys, please participate in the discussion. Do you have any question? Everything is clear? Can you give me any feedback?
It was clear for me.
Okay. The same for everyone?
Yeah.
Okay, great. So, yeah, someone said in the chat. Yes, okay, great. Please ask me question if you don't understand any part. I'll
It's
be
clear to
happy
me.
to answer.
I do have one question. Are there ever going to
Sure.
be trick questions on the tests where there will be an impossible domain and we have to identify that? Or should we assume that it's just going to be straightforward and possible every time?
No, it will be straightforward. Don't worry about that. Yeah. But I'm saying that when you model your optimization problems, you should be careful about that, because you don't want to have an empty in a feasible system, empty acceptable domain. So if the objective problem is simple enough, or we don't have too many constraints, even if it is complicated, we can use classical optimization. So it's not, I'm not saying, implying that classical optimization is not usable for very complicated problems. But if it becomes too complicated, we have the option to go for search rather than optimization, using classical optimization. But if it's not very complicated, it's straightforward to use simple classical optimization methods, such as this. For example, this function here is simple. We can easily find this minimum here. So this is minimum. You know, this is lower than this, right? This is minimum. And here also, assume it's a bowl. So it has two inputs. And it has one output, and this is the value of the objective function, this bowl. And here, as you see, this is the minimum. It's simple, but it's too if it's too complicated, such as this, too many local minimums or too many minimums here. Also this, it's too complicated, or too many constraints, too many restrictions. It's useful to use search. And we have we can do either grid search, also called brute force search. It means that let's divide the domain into some parts, small parts, infinitesimal parts or something, and then calculate the objective function in each part. For example, here in this example, we can divide it into some regions, and you take the middle of the function value at the middle of the region. And then you find something, the best solution, for example, here. Some option is that you do grid search. So as you see, you make a grid, and if it is two-dimensional, for example, if it is two-dimensional, your grid will be two-dimensional, right? Means like this. So on each node of the grid, you will search. The step of the grid is a hyperparameter. You should choose the step of the grid, the size of the grid. And then you search in the domain. Sometimes you see in machine learning, for example, they use grid search for finding the best hyperparameters using validation set. So, or brute force search, some kind of brute force. But you can do what?
Sorry, I had a question. Is it possible to apply a transform to the function to make it easier to find the minimum or the maximum? Like if you apply a transform, you could exaggerate certain features of the function, and then it would be easier to find potentially.
Yeah, that's a great question, but you should note that when you use a transformation, you need to know the inverse of it, because assume you transform it and it becomes simple, and you find the minimum. But so there are two things you should note. One of them is that, okay, let me make a note here. Just give me a sec. I think it was, yeah. No. Okay. Yes. Okay. So you make a transformation which is a monotonic transformation, like logarithm or something. Then it's acceptable. But if you make a transformation which drastically changes your local mean, for example, let me assume this is a function. You apply the transformation which becomes like this. You find this after this transformation, you find this as a minimum. However, it's as the transformation was not monotonic, it couldn't give you the actual local mean of before the transformation. So you should have some conditions on your transformation. Another thing you should note that in optimization, you usually have two goals. We will see that. Either you want to find the argument or the objective variable x star, or the f of x star is important for you. Okay, sometimes when you do, for example, assume I want to minimize f of x2 plus 2, for example. Yeah, let's say this function x minus 1 squared plus 2. Okay, what is x star? Is 1, right? At 1, it becomes minimum. Its function is like this. Function is like this. 1. This is 2. This is f of x. At x star is 1, but f of x star is 2. Usually, when you apply a monotonic transformation and you solve the optimization problem, it gives you the x star, and as long as your transformation was monotonic, the x star for after transformation is the same as x star before the transformation. Then you're done, if your goal is this. But sometimes your goal is also this. Okay, then you need to calculate f of x star before the transformation. So you will have another step. So you're not done when you solve the optimization problem after transformation. I wanted you to know these two things, difference between these two. Did you get my point?
Yeah, no, this makes sense.
Yeah. So you should note that which one of these is more important for you. If the second one is important for you after transformation, you find the x star, but you also need to put it back to the actual function in order to give the f of x star, or the cost. Okay. Again, as I said, the transformation needs to be monotonic in order not to drastically change the function in a way that the local mean or the answer is completely changed. And so again, if you have any follow-up question or any question, please let me know. So we can do search wisely in a way that we can have again meta-heuristic optimization. Rather than grid search or brute force search, we can have a wise search. For example, in this function, consider this function f of x versus x, and you you search here. You see this is the value randomly. For example, you see the function value here, and you see the function value here. And you say, okay, among these three, the value of function here is better. So this is better. Now let these two look around itself because it was the best. But these two move toward that better solution. So it's a kind of a wise search. We move toward that. And this is a meta-heuristic optimization. Usually the main idea behind all of them is this. So a good example for meta-heuristic optimization is that assume you have a room where there is a treasure under the ground. And assume we don't know where the treasure is. We are some people or particles, in other words. We randomly spread in the ground. And we say, okay, let's each of us dig some part of the ground. We do that, and after some search around each of us around ourselves, we find something. I say, okay, I found something, X something. Another person says, I found, for example, I say I found a pot. Another person says, I found, what do I say? A diamond, something. And we say, okay, I found several things around me. The best of me was pot. Another person found several things around herself or himself, and the best of them was, for example, a diamond. So we talk to each other, say, okay, I found this, I found this, I found this. Okay, now we say, who found the best among us? Someone says, I found a diamond, which is best among all of you. So we conclude that apparently treasure must be around that person. So, however, we say that, by the way, I found some pots. I'm saying to myself, I say, I found some pot. Maybe some treasure is around me too. However, diamond is more valuable. Therefore, I move to a little bit toward myself, to the best of myself. I found the pot at my left. I've moved a little bit to my left, however, more toward the best solution in that iteration, which is for example, the diamond. So I move in a vector, which is the linear combination of my best and the global best that we found in this iteration. And we move, all of us with some step, we move, the next iteration starts. We dig again. We dig around ourselves. We do this procedure repeatedly until we find some best treasure in the ground collaboratively. So this is how we search wisely in some landscape. And by the way, the objective function that we are either minimizing or maximizing is also called objective landscape or search landscape, whatever. If we are using search method, it's usually called search landscape. Why? Because it's exactly like a landscape. For example, if the cost function is 1D, one-dimensional, if you see it's like a valley or mountain, it's exactly like a landscape. If it is 2D, two-dimensional, it's like a bowl. How should I draw it? It's like a bowl with valleys. It's exactly like ground, the earth. The earth, if you consider the height of the mountains as a cost, then the earth is two-dimensional, but the cost is the third dimension, or the height of the mountains. So you have valleys and all of these things. You want to find the smallest valley, for example. So that's why we also call it landscape. Now let's go to sets and norms. So we have interior, closure, and boundary. Okay, assume that we have a set D. I call it D. And usually I denote a set using fancy letters, capital fancy, like this here. If it is a regular set, if it is a standard set such as this is the real numbers, right? The font is like this. And this RD means the D-dimensional Euclidean space. What does it mean? For example, this is two-dimensional Euclidean space. This is three-dimensional Euclidean space. So D-dimensional Euclidean space means we have D variables. And the point X in this set is an interior point of this set. What does it, for example, consider this? This is a set. And I consider inside of it as the interior, but not the boundary of it. As you say, this means there exists, some epsilon which is positive, where y, it's the set of y's. It means that all of the points y, set of y's like this, a point y, where y minus x, this means the distance of y minus x. So consider as you said, so this is the point x. For any other point y minus x is inside the set. So it means the difference of them, where it is less than epsilon, is inside a subset of D. What does it mean? For example, if a point is on the boundary, then this condition is not satisfied. Or if it is outside of the set, it's not satisfied. In simple words, if you don't want to look at this, I'm drawing it here. It means that if it's a set inside of it, excluding the boundary is the interior of this set. Now, some other concepts. So we have the boundary of the set, which means exactly the boundary. And what is the closure of the set? The closure. It means that the interior, I can also look at this definition, interior and the boundary, their union. This is union. It means that both interior and the boundary. And you can also look at it from here. It means that the whole Euclidean space, which is this, the whole Euclidean space, this is excluding, this is minus, excluding in the set, for sets. Excluding, what is this? This is the whole thing minus D. So this is D. The whole thing minus D is this here. The interior of this is this exactly. So the boundary is not covered. Everywhere minus this means exactly D including its boundary. So this is called closure. Closure means the set including its boundary. And boundary means closure minus the interior of the set. Only the boundary of the set. These are the concepts to know about the sets. Now, convex set and convex hull. So what is this? It means that convex set, it means that, but let me first tell you this. Let's consider 2 points, X and Y. This point is Tx, this point on a line connecting X to Y is Tx plus 1 minus Ty, where T is between 0 and 1. Why? I'll tell you why. If put T to 0, this term is 0, this becomes Y. It means that we are here. For T0, we are exactly here. If we set T to 1, this term is 0, this means that we are exactly here on X. And for T between 0 and 1, we are on the line between X and Y. If T is less than 0 or greater than 1, it means we are here. And if T is all R, it means that the whole line connecting X to Y, passing through X and Y. So this means the line connecting X and Y this means for all. For all points X and Y inside the set D, and where T is between 0 and 1, as we talked here, this means that all the line connecting X to Y should be inside D. If I look at this figure here, for example, consider any 2 points, any 2 points inside this set. If we connect them together, Tx plus 1t minus y is inside this set. You can't find 2 points where the line connecting them is not inside D. This is a convex set. Non-convex set is like this. I have found 2 points, at least 2 points, where the line connecting them is not completely inside the set, as you see here. So this is a non-convex set. In other words, in very simple words, a convex set is a kind of a bumpy thing. A bumpy, it doesn't need to be round. It can be like this. This is also convex. But as you see, it's a bumpy. But if a part of it is not bumpy like this is not convex anymore, because you find 2 points where the line is done. It's a bumpy thing. It covers itself. It's as I think it's obvious what I'm saying. So convex hull simply means that if you have a non-convex set, the smallest set around it which can make it convex, this is convex Hall. For example, this set, which is non-convex, the smallest set around it, which makes it convex, is this. Because this part that I'm drawing is already convex. The only part which is not a non-convex is this. So I draw this. This is a convex hollow of D. In other words, we are convexifying the set. We are making it convex. This is convex hull. So minimum, maximum, infimum, supremum. So look at this figure. I think it shows you everything. This is the minimum when you actually have the minimum. This is the minimum. This is maximum. I think minimum and maximum are very obvious to you. This is supremum, where you don't, for this function, it goes to infinity, right? And in infinity, it converges to this line, but it never reaches that. So it never has a maximum because it never reaches this. We call this upper bound, the smallest upper bound on the function, supremum. Maximum is a special case of supremum. So this maximum is also supremum, but this supremum is not maximum because we never reach that. Infimum, it means the largest lower bound. It never reaches that. Again, minimum is a special case of infimum. But infimum is not necessarily a minimum. That's why you sometimes see, rather than saying max f of x, you sometimes see in papers or things supremum of x, f of x. Why? Because they want to cover this case too. Maybe the function has some cases like this. We want to find that too. But if the function doesn't have such cases, then you can simplify this to this expression, supremum of f of x to maximum of f of x, or infimum of f of x to minimum of f of x. Again, I already explained that in what is infimum and what is supremum. Infimum is the largest lower bound. So as you see, this means the largest lower bound. For all domain of x, the z, which is the largest lower bound. This is lower bound, and this is the largest. And supremum is the smallest upper bound. Is everything clear, guys? Yes?
Yep.
Yeah, great. Okay. We still have some minutes left. We'll go until the end, and then we'll continue next session. So we have inner product of vectors. Consider two vectors, x and y. So these are, as I said, these are the column vectors, x1 to xt, d-dimensional, right? And y1 to yd. And these are scalars, these are numbers. And this is transpose, which means these are column vectors, and this means they are d-dimensional in the d-dimensional Euclidean space, right? And this means they belong to this set. They belong to the Euclidean space with d-dimensional Euclidean space. Their inner product, also called dot product, we denote it in this way or this way. And this means that the summation of their multiplication of their elements. I will give you an example. X is a two-dimensional vector of 1, 2. Y is a two-dimensional 3, 4. What is X transpose Y or X, Y? Means that what is X transpose? 1, 2, right? What is Y? 3, 4. And if you multiply these, it becomes 1 times 3 plus 2 times 4. It means 3, this is 8, this is 11. As you see, dot product or inner product gives you a scalar. The output is a scalar. It's a number, although its inputs are vectors. And I tell you this, and I think the session will be over. So inner product of matrices. Assume we have two matrices. And what does this mean? This means Euclidean, it means a matrix of D1 dimension by D2 dimension. For example, if you say R 3 by 2, it means the matrix with 3 rows and 2 columns, right? So, and as I said, we show matrices with bold capital letters. And Xij, let it be the ijth element of X. For example, X32 means the 3rd row and the 2nd column here. This is the X32. And what does this mean? We denote it with this. But we need a trace, a trace operator. Trace is nothing complicated. What is trace? Trace is it has some definition for eigenvalues, but I don't want to go to that definition. Simply, the summation of the diagonal of the matrix, because the input of trace is always a square matrix. So if it is 3 rows, 3 columns, it is 4 rows, 4 columns. It's a square matrix, and the diagonal, if you sum over the diagonal of the matrix, it gives you the trace. So the trace of, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9 is 1 plus 5 plus 9. Okay. And why do we need a trace operator here? Because X transpose Y is a matrix. Recall here, we have X transpose Y, but it becomes a scalar. X is a vector, Y is a vector, but X transpose Y becomes a scalar. Here, X is a matrix, Y is a matrix, but X transpose Y is not a scalar. It's a matrix again. We need to make it a scalar. Therefore, we need a trace operator for it when we have matrices. And trace, as you see, its output is a scalar. It's a scalar. And it means that you multiply the elements of X and Y all together. For example, if you have 2, 3, 4, 5, and you have 1, 2, 3, 4, you multiply these to each of these, plus multiply these to each of these, plus multiply 4 to each of these, plus multiply 5 to each of these, and then you sum over all of them. It's inner product of matrices. And as I say, trace has some formal definition, but I think the simple definition is that it is proof that it's equivalent to the summation over the diagonal of this matrix. So these are the inner products. And what, just one more thing, and it will be over. What visually, I mean, visually, if you have 2 vectors, X, Y, for vectors I'm talking about, you project the vector Y to X, it means that it's perpendicular, write a line which is perpendicular, and this vector, this amount is a projection of Y onto X. This is a vector, again, a vector. So this is the vector X, the whole thing. This is the vector Y. When you project Y onto X, it means that you make a line perpendicular on X from Y. You get another vector, which is this. And if you take the length of this vector, it's equivalent to X transpose Y or Y transpose X. Doesn't matter. They are equivalent. So you can say inner product is the length of projection of one of the vectors onto the other one. Again, you can project X onto Y and get this length. These two lengths are equal. So yeah, this is inner product and what it means. Any question before we end the session for today? Was it clear, guys? Can you give me any feedback?
Yeah, one
Yeah,
question.
it was.
What?
Can you hear me?
Yeah, it
there?
was good.
Yeah, it was clear.
Okay, great. I hope you enjoy that. These are the concepts that you might say, how are these related to optimization? But these are the concepts required for optimization. And we'll have a lot of fun. Next session, we'll go over the rest of these slides, and then we go to linear programming. And linear programming is much simpler, I think, than what you might think of. It's simpler than these concepts. It's very, it has tables. We'll have fun. We had some procedures. We'll go and say, okay, we write tables and how to solve them using tables. That's why it's called Tableau method. So it's not very complicated. We will cover this, and then we'll go over the linear programming, and the session afterwards we'll go to integer linear programming, and after ongoing. Okay, great. If there is no question, please let me know if there is any question. Otherwise,
Yeah, I have one
we
question,
can
Ben.
end. Yeah, sure.
Can you open that slide again, the inner product one?
Yeah, just give me a sec. This?
Yeah. So for inner product of vectors, the output will always be a scalar, right?
Which one?
For the
Yeah,
inner,
yeah.
and for the inner product of matrices, we are using a tracer in order to convert the output into a scalar.
Exactly.
So is it mandatory to have the output in scalar?
The output of inner product is a scalar.
Yeah, but
So
in
always
matrices,
it's
yeah, like the question is, in inner product of matrices, we are using a extra variable or tracer in order to convert the output to scalar, right?
yeah. But by the way, this is the definition. Okay, you can compute. You can multiply x trans x. So you can calculate x transpose, multiply it by y, take the trace, or you can use this. They are equivalent. You will get the same number.
Same number. Okay.
You can multiply all the elements of x and y and sum them, or you can calculate x transpose. So you transpose x and then multiply it by y and get the trace, and only sum the diagonal of x transpose y.
Yeah.
You will
prefer
get the
to-
same number,
output.
the
Yeah.
same value as. Yes.
Cool. Thanks.
Did you get? No
Yeah.
problem. Okay. Any other question? Okay, guys, thanks. It was great. I think we had great session, and we'll see you soon in the next week. And I will also go and have a chat with your TA and discuss the assignments with your TA, and then we'll let you know. If there is no any question, okay, thank you. Thank you for attending and
Thank
listening
you for your
and
time.
having
Thank you.
this. Thank you very much.
Well, thank you very much.
Thank you. Thank you very much.
Thank you.
Thank you. Bye.
Yeah, bye.
Thank you. Bye. Thank you very much. Thank you.